I'm very glad to be here to share our recent research on multifunctional additive manufacturing of 4D printing. So 3D printing is a well-known manufacturing technology, and if we look at the evolution of the 3D printing applications, actually we can summarize as 3 levels. First is just a visualization. So we use 3D printing. We can create the real 3D structure from the CAD model. And at this level, we just care about that appearance, color, surface finish, something like that. And the second level, people use that 3D printing the structure as the structural components, and then we are more interested in the properties such as stiffness, strength, stability, and those mechanical properties. And then nowadays, we have introduced a lot of new functionalities into 3D printed structures, such as like actuation, conductivity, and many others, right? So therefore, now the 3D printing has been like has been into a new area, which is the multifunctional additive manufacturing. And 4D printing is one of the, I think, one of the most typical example of the multifunctional additive manufacturing. And what is 4D printing? So before we talk about 4D printing, we need to know a kind of material, which we call that smart soft material, such as like shape memory polymer, hydrogel, liquid crystal elastomer. Those materials, when we apply environmental stimuli, this material will exhibit like a large deformation. And then when we print we do the 3D printing with the smart soft material, then we can create that the 3D printed structure that can change shape over the 4th dimension time. So therefore, we can there are 2 pioneering examples. One is presented by the Professor Stent from MIT, and the other is from Professor Jerry Chee's group, and I was the first author on the paper. Now, why is that 3D printing with the hydrogel? The other is 3D printing with a shape memory polymer. All the structure can change shape over time. So, what I just introduced, what is the smart soft material? So, in general, that this material can sense that the environmental stimuli, and then it will respond. Like the response is that the property change. So the environmental stimuli there will be a lot. Then also the property change, in general speaking, there are a lot, can be like a change in shape, change in property, and a change in functionality. And in recent years, our group has been working on, those kind of the change. And I want to show a few examples. One is that the most basic example is a change in shape. So we can like print 3D structure with shape memory polymer, and then the printed structure can change the shape over time when we apply like the heat. And the other is that also we can change property. For example, shape memory polymer, it can not only actuate, but also the modulus can change. Once the material is in its glassy state, the modulus is very high, like at 1 gigapascal or even higher. And then the material is at the rubbery state, the modulus is very low. So basically there will be like a 3 order of magnitude stiffness change. Therefore, if we apply that the shape memory polymer with a soft actuator, actually we can make like the soft actuator that can change stiffness. So then the soft actuator cannot only to carry a lot of different geometry, but it can also carry heavy load. Now, one more example is that the change in color. So we can like print some interesting material which the color can change, or overheat. Or we can also use like the 2-photon to print some we call that the structural color. So then once we apply that load, those structures are deformed, and then the pattern would be disappear. And then we use that shape memory effect. We can trigger that shape memory, the recovery of those structure. That would like show the color, and then we will recover the pattern. And also, if we print some material which is electroconductive, and then once we apply the load onto the material, actually we will see that the signal change. But I will show some detailed example, from our group, and but due to the time limitation, there would be a few. And but before I introduce that our group's example, I want to talk a little bit about that the 3D technologies for printing soft materials. There are a lot actually, like a PolyJet, where the pioneering work was made by the PolyJet printer, or like a DIW, direct ink writing printer, extrude the material from the nozzles. And also there is another one, it's called the digital light processing. So compared to the other digital light processing-based 3D printing, or we call DLP, which print 3D structure, is that if we have a 3D model, we first slice the 3D model into 2D patterns, and then we send those 2D patterns to a DMD, a projector, and the projector would like shine that the UV light with the corresponding patterns, and then focus onto that the surface of the polymer resin, and then it would trigger the localized photopolymerization, and then like create that the solid patterns layer by layer, and then we can create a 3D structure. Using this technology, actually, we can print the structure with high resolution and also multiple scales, and then compare with different 3D printing technologies. Actually, DLP shows the following advantages, such as like fast speed, high resolution, and can create highly complex 3D structure, can create a structure with high resolution and a larger area. Also, DLP is compatible with a wide range of printable materials, such as shaped membrane polymer, hydrogel, and many others. And we use DLP to print a lot of material, and also we develop a lot of high performance material which are compatible with DLP. For example, we develop a UV curable shaped membrane polymer, for DLP-based 3D printing, and to address the problem that for the earlier shaped membrane polymer-based 4D printing, which had less, failure strength, and we develop a mass accurate-based shaped membrane polymer system. So because all the monomer and cross-linker are chemically available, and we just need to buy them from the company, and then we can. So this material is highly tunable for some mechanical properties, and also the material exhibits large deformation, so it can deform by more than 300%. Also, because this material is compatible with DLP-based 3D printing, therefore we can print a very high resolution. And for example, the highest resolution achieved is 30 micron. But this material is mass accurate based. The meso functional group actually would make the chemical reaction quite slow. And then we also develop a new material system, which we call that the UV curable and mechanically robust shaped membrane polymer for 4D printing. The monomer is just tert butyl acrylate, and we use a special cross-linker, which is called aliphatic uracil diacrylate. So using such a material system, actually, it shows good suitability for DLP-based 3D printing, have a moderate viscosity and a fast curing speed, much faster than the mass accurate-based shaped membrane polymer. And also, more importantly, it exhibits excellent mechanical and printing capability. For example, now we can deform the shaped membrane polymer with very large deformation. It can be stretched by 1,240%, and also have a good shape recovery, shape fixing, and shape recovery ratio. So we apply the heat, and it can quickly recover to its original shape. And because it's compatible with DLP, and we have a very high resolution DLP printer, we can print that structure with very high resolution. So high resolution is the highest resolution up to 2 micron, and we can print a very highly complex 3D structure. And also this 3D structure exhibit excellent, mechanical property. You can program it into very very complex, it can sustain large deformation, and then we squeeze it into a sheet, and then you put it into hot water, it recovers quickly. And more importantly, we can tune that the thermal mechanical properties by simply change that the cross linker, and also as I say that it shows good shape fixing and the recovery ratio, and more importantly, this material exhibits excellent capability of sustained cyclic loading. So we apply that the mechanical load at its rubbery state, from 150% to 250%. The material can sustain more than 10,000 cycles without finding any failure. So this is an excellent material. And also we show some demonstrations how to use this material. One is that we 3D printed, we call it the smart furniture. We printed some like the smart hinge. And then we have such a table, when the table is we just, it's in its storage state, we just, we can bend that the legs, and then it will be in a small volume. And then if we want to use it, then we just apply heat, then the leg will expand quickly. Okay, and then this table can carry heavy load. Another is that for that we call it the self-deployable solar cell system. We print a smart hinge where we leave some channels, and then we can apply that conductive wire into these channels, and then we apply that electricity to generate the dual heating, and the dual heating would trigger that recovery, and then it would have a potential application for that the aerospace. And for example, here we have the solar panel, and the solar panel is first folded, and then we apply the electricity, and the solar panel expands. And then the solar panel would collect the solar power, and then to generate the electricity. Okay. And another material I want to share with you is that hydrogel. Hydrogel is a well-known and well-studied material, which can absorb water and contain a large amount of water, but does not dissolve into water. And hydrogel has found many applications, especially in like the bioengineering, soft robotics, and like the flexible electronics. And we develop an approach to make, to print some hydrogel structure, which with a high water content and excellent mechanical property. The way we do is that we convert that the commercial photo initiator, such as TPO, which is normally not water soluble, and now we develop an approach to make it water soluble. Therefore, we can print some the hydrogel system, actually as like Acrylamide-based hydrogel system, which has high water content, like more than 90% water. And we having such the hydrogel precursor, and then we use a DLP 3D printing. We can print like a high resolution hydrogel network. The grid, the width of the grid is up to 7 micron, and we can print a very complex 3D structure, such as a carbon foam. And also this material, this hydrogel exhibits excellent mechanical property. It can sustain like a large stretch or compression. And more importantly, we combine this hydrogel with our multi-material printing system, and also combine. Then we find that our hydrogel actually can to form a very strong bonding with a lot of different materials, such as like elastomer or like a rigid polymer. So therefore, we can print a structure which half is hydrogel, half is elastomer, and this structure can sustain large deformation, and there is no debonding in the interface. Also, we can print like a rigid hydrogel and elastomer, and we stretch. There is no debonding. And we also investigate that the interfacial property between the hydrogel and the other polymers, and we find that actually the interface is stronger than the hydrogel itself. Therefore, the hydrogel breaks rather than the interface. And also our material, our method shows very good generality. So this material can be applied to a lot of, we can print our hydrogel with a lot of different polymers, such as like Tango, Vero, or like a soft material, rigid material, even like ABS material or shape member polymer or PAC-DA, or all of these, we can print the hydrogel with, okay. And then we show a few applications. For example, we can print a lattice structure reinforced hydrogel composite. So we can print a hydrogel where we have that the rigid lattice structure to reinforce it. And also it is 3D printing. Therefore, we can control that the diameter of the lattice. And by controlling that the diameter of the lattice, actually we can control that local stiffness. Therefore, we can like change the stiffness of this lattice from like a pure hydrogel, which is only like maybe a 10 kilopascal, to like the part where we have like the bigger lattice, and then the modulus can be changed to 5 megapascal. Another example is that we can combine that the hydrogel with shape memory polymer. Shape memory polymer, we can print that as a shape memory polymer stent for the cardiovascular application, and then we add that hydrogel onto those stents, the rod of the stent, and then hydrogel can be used for the drug releasing application. Therefore, we can have that stent which is not only able to expand, narrow the blood vessel, but also those hydrogel will release the drug. Therefore, we add like 2 functions into one stent. And also hydrogel, if you add that the salt into hydrogel becomes like electroconductive, and then if we do the printing, we can print that the hydrogel circuit. And if we print the hydrogel circuit onto a actuator, actually we can make that the actuator able to sense the deformation. Therefore, we can have that when we have that actuator, we apply that the air, right, the actuator band, and then once the actuator band, we will find that the resistance change, and then we will know that how much that the actuator bends. And also we can print, because we can do the printing. We can also print those circuits onto a glove. Okay, then we can print a smart glove, and then once we do the calibration, okay, then we can use such a glove to control a magnetic finger. And okay, I still have maybe a few minutes. And the last I want to share is that called the direct 4D printing. Okay, a direct 4D printing means that if we print a 2D pattern and then you apply a stimuli, and then the 2D pattern will evolve into 3D structure. Okay, for example, like Jennifer Lewis or like Professor Jerry Chi or Professor Danning Fang, or they also demonstrate a very excellent work on the direct 4D printing, but the material they use is hydrogel. Okay, using that shrinkage or swelling of hydrogel. But the challenge is that hydrogel is normally quite soft, and the modulus is very low. So those are just for demonstration. Okay, you cannot use that for any application. And when we study with that our acrylamide hydrogel, we find that the hydrogel, once it loses water, you can not only see that there's a large like the volumetric change, but also the modulus changes a lot. When the hydrogel with high water content, the hydrogel is very soft, like maybe just a 7 kilopascal. But when the hydrogel loses its water, okay, actually there will be a glass transition happens in the hydrogel. So hydrogel would go into the glass transition, and then the modulus is very high. There would be more than 1 kilopascal, actually gigapascal. It would be like 3 to 5 gigapascal. Therefore, the dehydration is a process which is shape change plus stiffness change. And then we use this, combined with our multi-material 3D printing system. Actually, we print hydrogel with elastomer, and then once hydrogel lose water, it would create a banding. Okay, then we can, it would create a bending. If we design some structure, we can make a 2D structure become a 3D structure. But also, as I mentioned earlier, there is not only shape change, but also like the stiffness change. The printed structure also can carry heavy load. Okay, we also do a lot of like characterization and do the modeling, which would help us to design, to find the right parameter to get the right curvature we want. Okay, and also we also implement our like the theoretical model into a finite elements model to write a UMAT code, and then it would guide us to design the 3D structure. Okay. And also this compare with other like because ours is direct 4D printing, it saves a lot of time, and also compare other material. Our material, it has very high stiffness, not only at room temperature, but also at high temperature. Okay, that's all I want to share, and I would like to thank my group member, also my collaborators. Thank you very much.